Hello there, and welcome to the Sleep Well channel. I'm so glad you found your way here. Maybe you've had a long day, or perhaps you are simply the kind of person who finds peace in contemplating the deep structures and profound mysteries of the cosmos rather than wrestling with the everyday. Either way, tonight's slow, gentle journey is for you. You have nothing to do now but rest. Let your breath deepen your body, grow heavy, and your thoughts drift from the near and immediate to the far and eternal. Tonight, we are venturing into the quietest, heaviest places in the universe, black holes. These aren't just empty voids. They are the ultimate expression of gravity, silent monuments to collapse, where the very fabric of space and time is stretched and folded in ways our minds struggle to grasp. We seek to understand these invisible titans not with urgency or alarm, but with the calm curiosity they deserve. We will trace the edge of what we know, peering into the silent heart of the unknown, one gentle cosmic truth at a time. This journey is designed to be a lullaby, a quiet whisper of science leading you toward deep rest. One of the most fundamental truths is that a black hole is not an object you can observe, but rather a region of space-time where gravity is so intense that nothing, not even light, can escape its grasp. It is the perfect irreversible trap, a consequence of mass compressed into an impossibly small volume. The phrase black hole is a brilliant descriptor, acknowledging the absence of visible light, but the reality is more about an extreme warp in the geometry of the universe. When you imagine one, do not picture a dark sphere floating in space, but rather the visible effect of an invisible distortion, a whirlpool in the fabric of existence. Everything we discuss flows from this single, terrifyingly simple fact: here gravity wins completely and absolutely. The surface of no return surrounding a black hole is known as the event horizon. This is the critical boundary where the escape velocity exactly equals the speed of light. Cross this boundary and your path is sealed. You would need to travel faster than light itself to return, which is impossible. From the outside, an observer watching something fall toward it would see the object slow down and turn red as its light stretches, eventually freezing forever, just slightly outside the boundary, blurred and faded by time dilation. For the object falling, however, the journey continues, normally blissfully unaware that it has just crossed the most significant threshold in the cosmos. A black hole is often said to possess no features, meaning its ultimate state is characterized by only three external properties: mass, electric charge, and angular momentum, which is its spin. Everything else that makes up the star that collapsed to form it, its chemical composition, its unique structure, its entire history is swallowed and erased upon crossing the event horizon. This principle, sometimes called the no-hair theorem, simplifies the complexity of these objects dramatically. Regardless of how complicated a star was before it died, the resulting black hole is a clean slate defined by these three simple universal values. It is the ultimate cosmic economy, reducing complexity to its fundamental limits. The sheer mass of a black hole dictates the intensity of the gravitational tide that leads to the phenomenon of spaghettification. When an object falls toward a black hole, the gravitational pull on the side closer to the singularity is stronger than the pull on the far side. This difference in force stretches the object vertically while squeezing it horizontally, pulling it apart into a long, thin strand much like a piece of spaghetti. For smaller, stellar mass black holes, this stretching force becomes lethal long before the event horizon is reached. For the supermassive black holes at the centers of galaxies, the horizon is so wide that the stretching forces are more gentle, and you could potentially cross the boundary before the tidal forces truly crush your body. The innermost stable circular orbit marks the final safe resting place for matter spiraling around a black hole. Outside this radius, an object can orbit stably, even if perturbed slightly. Inside this boundary, however, no stable orbit is possible, and the matter inevitably spirals inward, across the event horizon, and toward the singularity. This radius is determined by the black hole's mass and its spin. For an observer watching matter fall past this final stable orbit is the final moment before its light is consumed forever, transforming a slow, elegant spiral into a rapid, final plunge. The only part of a black hole that can be directly observed and measured is its shadow. When light from behind a black hole passes near the event horizon, it is bent so intensely that it creates a dark circular region against the bright backdrop of the surrounding accretion disk. This dark circle is the black hole's shadow. The size and shape of this shadow are directly related to the mass and spin of the black hole, allowing astronomers to calculate its properties. The landmark image captured in 2019, which showed a black hole shadow, was the first successful observation of this phenomenon, confirming decades of theory with a glowing ring of light surrounding the ultimate darkness. This image provided the most profound evidence that these cosmic tyrants truly exist in the universe. The gravitational field surrounding a black hole is so immense that it drags and twists the very fabric of space-time around it. This effect is known as frame dragging, and it is most pronounced around rapidly spinning black holes. As space-time is twisted, anything moving through it, including light and matter, is forced to follow the rotational direction. This means that a gyroscope placed near a spinning black hole would not point in a fixed direction, but would be gradually pulled to rotate with the space-time itself. This twisting is a subtle yet powerful consequence of general relativity, showing that the universe's most extreme objects don't just warp space, they set it in motion. This quiet, ceaseless turning is a constant feature of the space that surrounds the invisible monster. If these calm, curious explorations help you unwind or give you a quiet way to end your day, consider liking and subscribing to the channel. It helps others find their way here too. One sleepy soul at a time. Now let's begin. We continue our quiet journey, drifting gently inward toward the extreme heart of the black hole, a place where gravity becomes absolute and the very laws of physics as we know them reach a quiet breaking point. Let your breathing settle and your mind soften as we explore the terrifying yet profoundly still center of these cosmic monoliths, moving slowly past the point of no return. Deep within that sealed region of space, the inevitable destination for all infalling matter is a point of infinite density, known simply as the singularity. This is not a star, a planet, or any form of physical matter we can easily conceive. It is a single dimensionless location in space-time where all the immense mass of the black hole is concentrated to zero volume. Here, space-time curvature is infinite and matter is crushed beyond any recognition of its former state. The singularity represents a total breakdown of Albert Einstein's general theory of relativity, as the equations that govern the universe cannot accurately describe conditions of infinite density. For the infalling traveler, this destination is absolute and final. Every single path through that warped space-time geometry points directly toward this singular point, making avoidance a mathematical impossibility once the boundary has been crossed. It is a quiet, profound testament to the power of gravity when it is allowed to proceed without any opposing force, a destination that is not an object, but a limit, the ultimate end of all physical structure. The crushing force of gravity near this core means that even the fabric of space-time itself loses its familiar properties. The very concepts of space and time are distorted. As matter falls inward, the spatial dimensions become warped and stretched. Time, which is usually experienced as flowing forward, can even take on a spatial quality, and the spatial dimension pointing directly toward the singularity becomes in effect a new dimension of time, an absolute one-way progression that cannot be reversed. This strange geometric exchange means that the concepts of forward and backward in space no longer apply in the way we understand them. There is only one direction, which is inward, downward, and toward the inevitable point of collapse. This subtle shift in the fundamental nature of existence is perhaps the most mind-bending aspect of the core, transforming the familiar universe into a geometry that is absolute, unmoving, and utterly unforgiving. The quiet reality is that the interior of a black hole is a region where the maps of existence are completely redrawn. Within a non-rotating black hole, mathematically described as a Schwarzschild black hole, the singularity is a perfect, unmoving single point. It has no size, no breadth, and no thickness. All the tremendous mass of the black hole is focused there, a pure, silent concentration of gravitational power. The physics here, though extreme, are simple. In their geometry, a perfect concentration of matter that exists only as a point of infinite power. This perfect, point-like structure simplifies the mathematics of the black hole's exterior, yet deepens the physical mystery of what happens when matter reaches such absolute concentration. The perfect stillness of a non-rotating black hole is echoed by the unmoving static nature of its core. Everything that falls in rushes toward this same infinitesimal location, the ultimate destination of all movement within that sealed region. However, the core within a rotating black hole, described by the Kerr solution, is theorized to be a ring or a circular loop. Due to the angular momentum of the original massive star, the singularity is stretched by centrifugal force into a one-dimensional circle of zero thickness. This ring-like structure is immensely fascinating because mathematically it suggests a hypothetical path through its center. While still representing a breakdown of known physics, the ring singularity presents theoretical possibilities like the existence of a naked singularity or even a wormhole, a theoretical tunnel through space-time itself. The quiet, constant spin of the black hole imparts this shape to its heart, offering a subtle yet powerful twist to the ultimate silent destination of all infalling matter. This rotation adds layers of complexity and possibility to the interior geometry. The Cauchy horizon is a theoretical internal boundary found only within a rotating black hole, lying between the outer boundary of no return and the ring singularity. Crossing the Cauchy horizon might lead to strange and profound effects where the concept of cause and effect breaks down, and events that were once impossible can suddenly become possible. It represents a boundary of predictability. The existence of this inner horizon suggests that the interior geometry of a spinning black hole is far more complex and dynamically layered than its non-spinning counterpart. The interior of the rotating black hole is therefore a quiet landscape of warped space-time layers, shifting physical laws, and potential theoretical instability. A dizzying architecture built of pure gravity and rotational energy. The concept of a naked singularity suggests a theoretical scenario where a black hole singularity is not hidden behind the protective event horizon. If such an object existed, it would expose the infinite density and the breakdown of physics directly to the rest of the universe, violating the foundational principle that nature protects the wider cosmos from these catastrophic points. This would directly challenge the cosmic censorship hypothesis, a principle formulated by Roger Penrose, which suggests that nature does not allow naked singularities to exist. The outer boundary is seen as nature's mechanism for protecting the visible cosmos from the chaotic breakdown of known laws that occurs at the center. If a naked singularity were ever observed, it would require a complete and quiet overhaul of our most fundamental understanding of gravity and space-time itself, representing a failure of our current cosmic models. The immense gravitational field surrounding the singularity means that light rays can actually orbit the black hole in a region known as the photon sphere or photon orbit. This sphere, located just outside the event horizon, is the closest stable orbit for a photon, where the extreme curvature of space-time forces light to travel in a perfect circle. Maintaining this orbit requires an intense, precise gravitational pull. A photon in this region is perpetually trapped, traveling in a perfect circle, visible to the external universe only if it happens to be nudged outward to escape or if it spirals inward toward the final plunge. The photon sphere is a testament to the extreme bending of light, a fragile, luminous ring encircling the ultimate darkness, a subtle sign of the gravitational tyranny within. Inside the event horizon, the singularity exerts a tidal force that is so extreme that the concept of matter as we know it becomes meaningless. At a distance from the singularity, the difference in gravitational pull across an object might be subtle, but as the distance shrinks, the force disparity grows, exponentially stretching and squeezing the object until it is ripped apart into a stream of fundamental particles. This is the mechanism for spaghettification. Even if you were not spaghettified before the boundary of no return, you would be stretched and disintegrated long before reaching the core itself. The fate of all matter inside the sealed region is absolute decomposition into the very fabric of warped space-time, a quiet final surrender to infinite pressure. The boundary of no return itself is not a physical surface, but a boundary of information, a gravitational horizon. Once an object crosses it, all information about that object, its chemical state, its velocity, its unique form, is in a sense lost to the external universe. The singularity, however, is the final physical destination where the mass is truly stored, compressed to a point. The event horizon is the point where the future of the object is irrevocably sealed, but the singularity is the final crushing outcome of that sealed fate. They are distinct concepts, yet intrinsically linked by the irresistible absolute force of gravity. The boundary is the promise, and the core is the fulfillment. The entire journey toward the singularity within a black hole is a silent descent into space-time geometry. An infalling object doesn't feel itself accelerating toward a specific goal, but rather feels itself simply following the most natural path through increasingly warped space. Near the singularity, the warping is so severe that escape velocity, which is usually calculated as a speed, becomes an absolute direction pointing only inward. The trajectory of the infalling matter is simply the most direct line through the curved space, and that line leads only to the point of infinite density. It is the destination defined by the curvature of existence itself. If a spinning black hole's singularity is indeed a ring, theoretical physics suggests that it may be possible to pass through the ring without being instantly crushed, potentially leading to hypothesized new regions of the universe. This theoretical passage, however, would likely require incredible, unattainable precision and energy, and the physics surrounding the ring singularity are still hotly debated and may be inherently unstable. The concept is pure speculation, but it continues to fuel the imagination of physicists who seek to use black holes as potential natural gateways or portals. The theoretical geometry here offers a tantalizing yet potentially lethal loophole in the fabric of existence, a doorway in the ultimate darkness. The volume enclosed by the event horizon does not shrink to zero, even though the mass is concentrated at the core. If you imagine the space itself, the area within the event horizon still represents a certain quantifiable volume of warped space, but the mass that creates this warping is concentrated at the center. This strange feature of black hole geometry means that while the core is a dimensionless point, the gravitational effect defines a wide region of space. The black hole is therefore mostly empty space, but it is space that is utterly dominated by the gravitational presence of the infinitesimal point at its heart, a massive void defined by a single point. The information about what falls into the black hole is theoretically preserved on the event horizon itself, a phenomenon connected to the concept of black hole entropy. Although the principle suggests the information is lost, quantum mechanics suggests that information cannot be truly destroyed. Stephen Hawking theorized that the event horizon contains information related to the object's mass charge and angular momentum encoded on its surface area. This idea led to the development of the holographic principle, which suggests that the three-dimensional universe we experience could be encoded on a two-dimensional surface. The event horizon is thus seen as a quiet, silent screen holding the quantifiable memory of everything it has consumed. The singularity itself is not a feature of classical physics, but a mathematical requirement of general relativity when matter collapses past a certain point. Physicists anticipate that a complete theory of quantum gravity, one that successfully merges the large-scale physics of general relativity and the small-scale physics of quantum mechanics, would replace the singularity with a finite quantifiable region. This ultimate theory would resolve the issue of infinite density and space-time breakdown, likely describing the core of a black hole as a region governed by quantum foam, or another extreme yet finite state of matter energy. The singularity, therefore, is not the final answer, but a quiet, powerful signpost pointing toward the physics of the far future. We let these profound, silent truths about the absolute heart of the black hole settle gently in our minds. The singularity, a point of infinite density, a warping of time and space, a place where geometry becomes destiny, remains hidden, a quiet, absolute secret held in the depths of the cosmos. As we drift further into the night, we turn our attention to the immediate effects of the boundary of no return, where our normal conception of time begins its slow, strange decay. We shift our quiet focus once again to the critical gravitational boundary, the event horizon, and explore the strange, slow magic it works upon the flow of time itself. Let your body relax completely, releasing any tension you may be holding, and imagine yourself floating toward this immense, invisible threshold where perception and reality quietly begin to diverge. The boundary is defined by an absolute one-way passage. It is often compared to a waterfall outside this region. You can still swim against the current and escape, but once you cross the speed of the current, the flow of space-time toward the core is greater than the maximum speed you can achieve, the speed of light, making escape impossible. The event horizon is a sphere of no return, a gravitational trap so perfect that even a light beam aimed directly outward will inevitably be caught in the intense flow of warped space and redirected inward toward the central singularity. This boundary is not a physical wall, but a limit of physics, absolute silent and entirely defined by the geometry of gravity. One of the most striking mind-bending effects near this boundary is gravitational time dilation. Time, as measured by an observer far away from the black hole, appears to flow slower and slower for an object approaching the event horizon. This is because immense gravity warps space-time, causing a measurable slowing of all processes, including the ticking of a clock. A clock near the black hole would tick at a visibly slower rate than a clock on Earth. This effect means that an observer far away would never actually see an object cross the event horizon. They would only see its descent slow down, its light redden and dim, until it is effectively frozen forever, just slightly outside the boundary, blurred and faded by the passage of cosmic eons. For the infalling observer, however, time flows perfectly normally. They would not notice anything unusual about their own clocks, their own breathing, or their own sensation of time as they cross the boundary of no return. There is no physical sign or sensation to mark the moment of no return. Their world continues as it always has. It is only the outside universe that seems to warp and slow down, appearing to the infalling observer, as if the entire cosmos were speeding up dramatically toward their eventual final moment. The point of no return is therefore an unsettling matter of perspective, absolute from the outside, but utterly seamless from within, a quiet deception woven into the fabric of reality. The sheer size of the event horizon is directly proportional to the mass of the black hole, a relationship defined by the Schwarzschild radius. For every unit of mass added to the black hole, the radius of the event horizon increases linearly. This means that a more massive black hole possesses a larger, gentler boundary. If the Earth were hypothetically crushed into a black hole, its event horizon would be about the size of a marble, just under 1 centimeter. Conversely, the supermassive black hole at the center of the Milky Way has an event horizon millions of times larger than the Sun. This simple, proportional growth is a key feature of black hole mechanics, illustrating the vast difference in scale between the tiny, powerful stellar remnants and the immense galactic anchors. The event horizon is the theoretical surface upon which black hole entropy is said to be encoded. In a profound theoretical link, physicists proposed that a black hole has entropy, a measure of disorder that is directly related to the surface area of the boundary itself. The area of the event horizon represents the maximum amount of information that can be stored in that specific region of space. This concept led to the discovery of a foundational entropy formula, one of the most critical ideas connecting the seemingly separate realms of gravity, thermodynamics, and quantum mechanics. The event horizon, therefore, is not merely a boundary of fate, but a quiet, silent screen holding a quantifiable memory of everything it has consumed, a repository of cosmic data. The boundary of a rotating black hole, described by the Kerr solution, is actually double-layered an outer event horizon and an inner boundary known as the Cauchy horizon. The outer boundary is the familiar point of no return. The inner boundary, however, is a more mysterious threshold beyond which the predictability of space-time might break down. The double-layered nature of the rotating black hole's interior results from the combined effects of extreme gravity and the centrifugal force of its intense rotation, making its internal structure far more intricate and theoretically complex than its non-spinning counterpart. The existence of these layers reveals the subtleties of rotational effects on space-time geometry. The size of the boundary is minuscule for a stellar mass black hole, meaning the tidal forces are devastatingly strong near the boundary. For a black hole with the mass of our Sun, the event horizon is small, and the gravitational gradient, the difference in pull across a short distance, is so great that the tearing force, or spaghettification, begins long before an object reaches the actual horizon. Conversely, the event horizon of a supermassive black hole is so vast that the gravitational gradient is much shallower, allowing objects, in theory, to cross the threshold relatively intact, at least temporarily. The size of the event horizon directly dictates the gentleness or violence of the final plunge. The boundary quietly shields the singularity from the rest of the universe, a concept enforced by the cosmic censorship hypothesis. This hypothesis suggests that every singularity formed from gravitational collapse must be hidden behind an event horizon, thus preventing the rest of the cosmos from seeing where the laws of physics are fundamentally violated. The boundary acts as a cosmic veil, maintaining order and predictability in the visible cosmos. If a naked singularity were ever found, this fundamental principle of natural law would be broken, necessitating a complete revision of our understanding of the universe's inherent stability. The event horizon is constantly growing as the black hole consumes matter or merges with other black holes. Mathematically, the area of the event horizon can never decrease. It must either stay the same or increase. This rule is often referred to as the second law of black hole thermodynamics, mirroring the second law of regular thermodynamics, which states that entropy or disorder can never decrease in a closed system. This constant growth, even after merging, means that the universe's black holes are quiet gravitational gluttons, always expanding their dominion one gentle final sip of mass at a time, continuously increasing their surface area and their stored entropy. The boundary is the direct target for the Event Horizon Telescope's observation. Since the black hole itself is invisible, the array does not photograph the black hole directly, but images the silhouette it casts against the glowing gas surrounding it. This dark silhouette, the black hole's shadow, is slightly larger than the event horizon itself, due to the extreme bending of light that orbits the black hole. The array's quiet focus is on defining the precise edge of this ultimate darkness, which in turn allows astronomers to precisely calculate the boundary's diameter and the black hole's mass. An object falling through the event horizon would never be able to communicate its experience back to the external universe. Even a final frantic burst of light or radio waves emitted just inside the horizon would be caught in the intense unidirectional flow of space-time and redirected toward the singularity. This absolute lack of information leakage is what seals the black hole's mystery. Whatever is happening inside the event horizon is a phenomenon divorced from our measurable universe, a perfectly quiet, sealed secret for eternity, a truly isolated state of existence. The boundary's perfect sphericity is only true for non-rotating black holes. For spinning black holes, the event horizon is oblate or slightly flattened at the poles due to the immense centrifugal force generated by the black hole's rapid rotation. This subtle flattening reflects the kinetic energy of the black hole and slightly changes the geometry of the space-time around it. However, because the rotation of black holes is confined by the laws of physics, the oblateness is not extreme, maintaining an almost perfectly smooth, quiet appearance from a distance. The event horizon is linked to the information paradox, the profound question of whether information is truly destroyed when matter falls in. Quantum mechanics suggests that information must be preserved, yet the event horizon seems to erase all features, but mass, charge, and spin. Stephen Hawking suggested the information might be radiated away very slowly through quantum emission, or perhaps encoded on the event horizon itself. This paradox is one of the most active and fundamental areas of research in theoretical physics, showing that the event horizon is not just a boundary of space, but a conflict point for the universe's most important physical laws. The size of the event horizon corresponds to the amount of time an observer has before the tidal forces become lethal inside the black hole. In the case of a stellar mass black hole with a small boundary, the curvature is so tight that spaghettification is almost instantaneous upon crossing. Conversely, a supermassive black hole with a large event horizon has a much flatter curvature across the boundary's diameter. An unfortunate traveler crossing into a supermassive black hole might have several minutes of normal experience before the tidal forces near the singularity finally take effect. The sheer size of the event horizon provides a temporary gravitational reprieve from absolute decomposition. We let the quiet power of the event horizon and its warping of time settle gently in our minds. The boundary of no return, the slow dance of light, the absolute silence of sealed information. This invisible threshold marks the boundary of our measurable world, a profound line in the sand drawn by gravity itself. As we drift further into the night, we turn our attention outward toward the spectacular luminous structures surrounding the black hole, the brilliant visible effects that betray the presence of the invisible. We leave the quiet sealed mystery of the gravitational boundary and turn our minds toward the spectacular, brilliant structures that surround a black hole in the act of feeding. This is where the unseen becomes profoundly visible, where gas dust and stars are drawn into a blinding, violent spiral that lights up the cosmos. Let your mind relax and your breathing slow as we witness the ultimate cosmic fireworks, all still and gentle in the immense dark. The most brilliant phenomenon associated with a feeding black hole is the accretion disk. This is a vast, swirling pancake-like disk of gas dust and stellar remnants that spirals inward toward the boundary of no return. As matter falls toward the black hole, it gains immense speed and kinetic energy. The particles within the disk rub against each other due to friction and intense magnetic fields, heating the gas to millions of degrees. This extreme heat causes the disk to emit tremendous amounts of radiation, primarily in the X-ray and ultraviolet spectrum, often quietly outshining the entire galaxy it resides within. The inner edge of this disk marks the innermost stable circular orbit, the final safe point before matter is destined for the core. When a supermassive black hole at the center of a young galaxy is actively consuming mass from its accretion disk, it forms a quasar. Quasars are considered the most luminous and powerful persistent objects in the known universe. A single quasar can emit more light and energy than all the billions of stars in its host galaxy combined. Because they are so intensely bright, astronomers can detect them across billions of light years, effectively looking back into the early history of the universe. Quasars are thought to represent a phase in galaxy evolution when the central supermassive black hole was undergoing rapid, immense growth, drawing in massive amounts of gas and stellar material. The presence of a quasar is a sign of a galaxy in its most active, brilliant, and energetic youth. Many black holes, particularly those in quasars and active galactic nuclei, produce highly collimated streams of energetic plasma called relativistic jets. These jets are launched outward from the vicinity of the black hole's poles, perpendicular to the plane of the accretion disk, often stretching millions of light years into space. The material in the jets travels at near the speed of light and is believed to be focused and accelerated by the black hole's intense magnetic fields. These jets are powerful enough to heat the surrounding intergalactic medium, subtly influence star formation in the host galaxy, and sculpt the structure of entire galaxy clusters. They are the quiet, powerful exhaust of the invisible cosmic engine at the core. The powerful magnetic fields threaded through the accretion disk are believed to be the primary mechanism for generating the black hole's visible power. As the disk spins, magnetic field lines are dragged inward and twisted around the black hole. This intense twisting action is what squeezes the jets into tight beams and critically transfers angular momentum outward, allowing matter to actually fall inward toward the boundary. This magnetic mechanism quietly and efficiently converts the gravitational potential energy of the infalling matter into the powerful radiation of the disk and the kinetic energy of the jets. Without these magnetic fields, the black hole would be a much quieter, less visible consumer, lacking the brilliant energetic signs of its presence. An active galactic nucleus is the general term used to describe the central region of a galaxy where a supermassive black hole is actively feeding and emitting vast amounts of non-stellar radiation. Quasars are the most luminous type, but the category also includes less brilliant examples like Seyfert galaxies and radio galaxies. The activity of the nucleus is directly proportional to the rate at which the central black hole is consuming matter. A galaxy with a quiet central black hole, like our own Milky Way, is considered inactive. Studying these active regions allows astronomers to understand the co-evolution of black holes and their host galaxies throughout cosmic time. The color of the accretion disk changes dramatically as matter spirals inward. In the outer cooler regions of the disk, the gas glows in the visible and infrared spectrum, often appearing red or orange. As the matter spirals closer to the event horizon, friction and compression heat the gas to millions of degrees, causing the inner disk to glow intensely in the ultraviolet and X-ray wavelengths, appearing bright white or blue to the eye. The resulting spectrum of light emitted by the disk is a composite of all these temperatures, providing astronomers with crucial data to map the physical conditions of the spiraling matter and the black hole's properties. The sheer size of the accretion disk is often immense, often stretching hundreds of thousands of times the diameter of the black hole's event horizon. While the black hole itself might be as small as a city or as large as our solar system, its luminous accretion disk can span distances comparable to planetary orbits, or even thousands of light years in the case of a quasar. These disks are vast, thin structures relative to their width, and their immense size makes them visible to telescopes across astronomical distances. The sheer scale of the disk contrasts starkly with the infinitesimal size of the singularity at its heart. The jets emitted by these active nuclei often heat the surrounding intergalactic gas, preventing it from cooling down and forming new stars. This regulatory process, known as feedback, acts as a crucial self-limiting mechanism for galaxy growth. As the black hole feeds, its jets blow away star-forming gas, which limits both star formation and the black hole's food supply, essentially shutting down the activity. This mechanism is crucial to explaining why some massive galaxies stop forming stars, slowly evolving from active spirals into quiet red elliptical galaxies. The black hole, through its energetic outflow, acts as a cosmic thermostat, keeping star formation quietly in check. A tidal disruption event occurs when a star wanders too close to a supermassive black hole and is torn apart by the immense gravitational forces. As the star is shredded, half of its material is flung back into space, while the other half spirals into the black hole, creating a temporary, spectacular flare of light that can last for months or even years. These events provide a unique way for astronomers to detect otherwise quiet, non-feeding black holes and study the physics of matter falling into extreme gravity. These events are rare, yet they are powerful transient bursts of light resulting from a sudden cosmic execution. The radio lobes associated with some relativistic jets are vast regions of glowing plasma far beyond the host galaxy. When the black hole's jets slam into the cooler, denser gas of the intergalactic medium, they create enormous balloon-like structures that glow intensely in radio wavelengths. These radio lobes can stretch for millions of light years, making them some of the largest single objects in the universe, quietly dwarfing the galaxy that created them. These lobes are quiet markers of a black hole's past activity, holding the memory of powerful ancient outflows long after the jet has dimmed or shifted direction. The immense pressure and density within the accretion disk can cause gamma-ray bursts to be launched near the event horizon. Long-duration gamma-ray bursts, the most energetic explosions in the universe, are often associated with the collapse of very massive, rapidly spinning stars, which form a black hole during their death. The formation of the black hole and its accretion disk is thought to power the ultra-fast jet that generates the burst tightly, coupling the star's collapse to the dramatic birth of the black hole. The brightness of an accretion disk is limited by a physical boundary known as the Eddington limit. This limit is reached when the outward pressure of the radiation emitted by the hot disk is exactly equal to the inward pull of the black hole's gravity. If a black hole tries to consume mass too quickly, the intense radiation pressure will push the surrounding gas away, effectively blowing the black hole's food source away and regulating its feeding rate. Most supermassive black holes accrete mass below this limit, but actively feeding quasars can sometimes exceed the limit, temporarily entering a state known as super-Eddington accretion. The central black hole in our own Milky Way, known as Sagittarius A star, is currently quiet, meaning its accretion disk is very faint. The black hole is consuming matter at a rate far below its maximum potential. However, evidence suggests that in the relatively recent past, only a few hundred years ago, it experienced a powerful flare, potentially caused by a large gas cloud or star falling toward it. This quiet monster is not permanently dormant, and if a sufficient mass of gas were to fall into its grasp, it could briefly reignite, lighting up the galactic core with a brilliant flare of X-rays and gamma rays. The X-rays emitted by the inner accretion disk are used by astronomers to precisely measure the black hole's spin. X-rays are emitted from the innermost regions of the disk, just outside the final stable orbit. The extreme gravity of the black hole causes these X-rays to be gravitationally redshifted and warped. The precise measurement of this warping and the resulting distortion of the X-ray light allows astronomers to determine the rotation rate of the black hole. This technique has confirmed that many supermassive black holes are spinning extremely rapidly, sometimes reaching nearly the speed of light. The power of the accretion disk and jets ultimately comes from the quiet conversion of gravitational energy into light and kinetic energy. Matter falling into a black hole's gravity well releases a tremendous amount of energy far more efficiently than nuclear fusion. Nuclear fusion converts less than 1% of mass into energy, whereas accretion onto a black hole can convert up to 42% of the rest mass of the infalling matter into energy before it crosses the boundary of no return. This remarkable efficiency makes black holes the most powerful natural energy conversion engines in the known universe, quietly transforming mass into blinding light. We let the quiet power and brilliant light of the accretion disks and jets settle gently in our minds. These magnificent structures, the most visible signs of black holes, are a testament to the fact that even the ultimate darkness can generate the ultimate light. As we drift further into the night, we turn our attention toward the life cycle of these objects, exploring how the smaller, more numerous black holes are born from the spectacular collapse of massive stars. We now turn our attention to the most common class of black holes in the universe, those born from the cataclysmic death of massive stars. These stellar remnants are the quiet, weighty successors of cosmic giants scattered across the galaxy, silent inheritors of their parent star's immense gravity. Let your body feel anchored and still as we explore the smallest, yet most densely concentrated of these gravitational singularities. A stellar mass black hole is formed when a star, roughly 20 to 25 times more massive than the Sun, exhausts its nuclear fuel and undergoes a core collapse supernova. During the star's long life, the outward pressure from fusion is precisely balanced by the inward pressure of gravity. When fusion ceases, gravity crushes the star's core. If the remaining core mass is greater than about 3 times the mass of the Sun, a crucial limit known as the maximum mass for a neutron star, no known force can stop the collapse, leading directly to the formation of a black hole. The minimum mass required for a stellar black hole is estimated to be around 5 times the mass of the Sun. While the remnant core must exceed the 3 solar mass limit, the supernova explosion itself ejects a large fraction of the original star's material into space. Therefore, the star must be significantly more massive to begin with, to leave behind a core heavy enough to collapse entirely. Black holes in this lower mass range are the hardest to detect, as their gravitational influence is more subtle, and their boundaries are smaller. Stellar mass black holes are believed to be vastly numerous throughout the Milky Way galaxy. Theoretical estimates suggest there could be tens of millions of these black holes scattered silently in the galactic halo and disk. However, because most are not actively feeding on nearby gas or companion stars, they are quiet and invisible, making direct detection extremely rare. These dormant black holes are a significant component of the galaxy's missing mass and quietly contribute to the invisible gravitational presence that shapes the motion of stars and gas in the entire galaxy. The first stellar black hole to be definitively discovered was Cygnus X1, a binary system where a supergiant star orbits an unseen compact object that emits powerful X-rays. The X-rays are generated as gas is pulled from the supergiant star onto the black hole's accretion disk, heating the matter to millions of degrees before it spirals into the event horizon. The mass of the unseen companion was calculated to be greater than 15 solar masses, well exceeding the theoretical maximum mass for a neutron star, confirming its identity as a black hole. This discovery in the early 1970s was a critical moment, confirming the existence of black holes predicted by Einstein's theory of gravity. When a stellar mass black hole is formed in a binary system, the supernova explosion can impart a sudden kick to the black hole, potentially disrupting the orbit or even ejecting the black hole entirely from the galaxy. These kicks are caused by asymmetries in the supernova blast, or the anisotropic emission of neutrinos during the core collapse. If the kick is large enough, the black hole becomes a rogue black hole drifting alone through interstellar space. If the binary survives the kick, the black hole begins a quiet gravitational dance with its companion star, eventually leading to accretion X-ray emission or the possibility of a future merger. Stellar mass black holes are also the source of short-duration gamma-ray bursts when they merge with a neutron star or a companion black hole. These mergers are among the most cataclysmic events in the universe, creating intense gravitational waves and brief, powerful bursts of high-energy gamma rays. These short bursts are believed to be caused when the matter surrounding the merger, such as the final core of a neutron star, forms a tiny, rapidly spinning accretion disk around the newly formed black hole, launching a relativistic jet that punches through the surrounding debris. The event horizons of stellar mass black holes are comparatively tiny, making them extremely dense objects. A black hole with 10 times the mass of the Sun would have an event horizon diameter of only about 60 kilometers, roughly the size of a medium-sized city. This small size means the gravitational curvature and tidal forces near the horizon are immense. This is why stellar mass black holes are the classic examples of spaghettification. Any object falling in would be ripped apart almost instantly. They are the most efficient compactors of mass in the cosmos, yet their effect is subtle until a star wanders too close. Stellar black holes can be found by observing the orbital dynamics of their companion stars. Even if the black hole is not actively accreting matter, its immense gravity influences the motion of nearby stars, causing them to wobble or orbit around a central point of mass. Astronomers use precise measurements of stellar wobble to detect these unseen companions by looking for the periodic shifts in the visible star's light. This method has allowed the discovery of several isolated black holes that were otherwise dormant and completely invisible to direct light-based observation. The most precise measurements of stellar mass black holes now come from gravitational wave astronomy. The Laser Interferometer, Gravitational Wave Observatory, and its partners have detected dozens of merger events involving stellar mass black holes. These observations have provided direct confirmation of the existence of black holes and offered unparalleled precision in measuring their masses, spins, and orbital dynamics. The gentle, immense ripples of space-time generated by these collisions are the most direct evidence we have of these heavy, silent objects. The largest stellar mass black hole discovered in the Milky Way galaxy, known as Cygnus X1, has a mass estimated to be around 21 solar masses. However, recent gravitational wave detections from merging black holes have found objects significantly larger with masses up to 90 solar masses, challenging the established understanding of how massive stars die. These oversized black holes are now part of the mystery of the mass gap between the most massive stellar black holes and the smallest supermassive black holes. The mass gap refers to a theoretical range of black hole masses roughly 45 to 135 times the mass of the Sun, where very few black holes are expected to form. This gap is predicted because stars in this mass range are thought to die in a theoretical event called pair instability supernova. During this process, runaway oxygen fusion causes the star to completely tear itself apart, leaving no core remnant to form a black hole. However, the recent detection of black holes within this range is quietly prompting astronomers to revise their fundamental models of stellar death and core collapse. X-ray binaries are stellar systems consisting of a black hole accreting material from a companion star, and these systems are categorized based on the size of the companion star. Systems involving a large, hot blue giant star are called high-mass X-ray binaries, while those involving a smaller evolved star are called low-mass X-ray binaries. The latter are particularly important as they are the primary source for accreting black holes and often reveal the black hole's presence through intermittent X-ray bursts caused by sudden accretion events. The X-rays emitted by stellar mass black holes are often observed in bursts or flares because their accretion disks are unstable. Gas in the disk heats up and spirals inward. But when the inner disk becomes too hot, it can suddenly eject material or flare up intensely, causing the X-ray emission to fluctuate dramatically. These rapid, energetic changes in X-ray brightness provide astronomers with crucial clues about the black hole's feeding patterns and the physical properties of its immediate environment, a restless, flickering signature of the small, energetic monster. The final form of a stellar mass black hole is influenced by the angular momentum of the original star. If the star was spinning rapidly, the resulting black hole will be a fast-spinning black hole with its event horizon oblate and its singularity stretched into a ring. If the star was spinning slowly, the resulting black hole will be a near-perfectly spherical black hole. The speed of the black hole's rotation is crucial, as rapidly spinning black holes are capable of launching more powerful relativistic jets and are a more efficient energy source. The most recently discovered class of stellar mass black holes are the ultra-luminous X-ray sources, which are X-ray sources that shine far more brightly than could be expected from a typical stellar mass black hole. Some of these sources are now thought to be stellar mass black holes consuming matter at a highly super Eddington rate, meaning they are consuming matter much faster than the radiation pressure would normally allow. These extreme feeders are challenging the accepted limits of black hole accretion and providing a valuable window into black hole physics at its most efficient and powerful. We let the quiet gravity of the stellar mass black holes settle gently in our minds. These are the most common black holes, silent relics scattered across the galaxy, their presence revealed only by the gravitational ripples they create or the X-ray light they briefly emit when they consume matter. As we drift further into the night, we turn our attention to the true giants of the cosmos, the supermassive black holes that anchor entire galaxies and define the cosmic structure. We now drift toward the silent, immense giants of the cosmos, the supermassive black holes, which reside at the heart of almost every major galaxy, including our own Milky Way. These behemoths possess masses millions or even billions of times that of the Sun. Feel your thoughts soften and your sense of scale expand as we explore these cosmic anchors where gravity reigns supreme and time stretches across unimaginable distances, providing the foundation for galactic structure. The central supermassive black hole in our own Milky Way is named Sagittarius A star, a gravitational giant with a mass of approximately 4.3 million times that of the Sun. This immense object is located in the galactic center about 26,000 light-years from Earth. It is currently dormant and quiet, accreting only a trickle of gas and dust. While it is not active enough to be a bright quasar, its immense gravity governs the precise orbits of stars in its immediate vicinity, providing astronomers with the most detailed view of a supermassive black hole's gravitational effects. The observation of stars orbiting this unseen point confirmed its nature beyond any doubt. Supermassive black holes are millions of times larger in the diameter of their boundaries compared to stellar mass black holes. The event horizon of the Milky Way's central black hole is about 17 times the diameter of the Sun, yet its mass is concentrated at an infinitesimal singularity. Due to this immense size, the gravitational gradients across the boundary are gentle, meaning a traveler crossing it would not immediately be spaghettified. This large, relatively flat event horizon is one of the defining characteristics that distinguish supermassive black holes from their smaller, more violently curving stellar cousins. The formation mechanism for supermassive black holes remains one of the greatest unsolved mysteries in cosmology. The question is how they grew to such immense size so rapidly in the early universe. One theory suggests they grew from seed black holes of only a few hundred solar masses, formed from the direct collapse of massive primordial gas clouds. Another theory proposes that they grew through the rapid and continuous merger of smaller black holes and constant accretion of gas in the dense cores of young galaxies. The discovery of high-mass quasars only a few 100 million years after the Big Bang suggests an extraordinarily efficient growth mechanism was at work in the cosmic dawn. These immense gravitational centers are found at the heart of nearly every large galaxy. The relationship is so pervasive that astronomers believe the formation and evolution of a galaxy are intrinsically linked to the growth of its central supermassive black hole, a concept known as black hole galaxy co-evolution. The mass of the central black hole is consistently found to be proportional to the total mass or velocity dispersion of the host galaxy's central bulge. This tight correlation suggests a profound feedback loop where the black hole's energetic outflows regulate star formation and growth throughout the galaxy's entire history. The immense gravity of a supermassive black hole can influence star formation thousands of light years away through the process of feedback. When the central black hole is actively feeding its accretion disk, emits powerful winds and relativistic jets that can blast away or heat the surrounding gas. This action prevents the gas from cooling and collapsing to form new stars, effectively regulating the star formation rate of the entire galaxy. This powerful regulatory mechanism is crucial to explaining why massive elliptical galaxies stop forming stars and quietly become red and dead over cosmic time. The most massive black hole ever detected found in a distant quasar possesses a mass estimated to be around 66 billion times that of the Sun. This ultra-massive black hole is an extreme example, a cosmic monster that defies easy explanation. Its immense size and extreme luminosity make it one of the brightest objects in the early universe, allowing it to be seen across billions of light years. Such extreme objects are the gravitational anchors of galaxy superclusters and provide unique laboratories for studying gravity in the most powerful extreme conditions. The orbits of the stars immediately surrounding a supermassive black hole are known as the S-stars, or the stellar cluster. These stars are observed to move in tight, fast, highly elliptical orbits around the unseen central mass, providing the most conclusive proof of the black hole's existence. The star S2 orbits the Milky Way's central black hole at a distance of only about 17 billion kilometers, 3 times the distance of Neptune from the Sun, at speeds of nearly 3% of the speed of light, completing a full orbit in just 16 years. These precise, quiet observations confirm the mass and location of the black hole beyond any reasonable doubt. Supermassive black holes grow primarily through 2 mechanisms: accretion, consuming gas and dust, and mergers colliding with and swallowing other black holes. In the early universe, accretion was likely the dominant growth mechanism, explaining the rapid growth of quasars. In the later universe, mergers between galaxies, which bring their central supermassive black holes together, become more significant. When 2 supermassive black holes merge, the resulting gravitational waves are the most powerful in the cosmos, potentially detectable across the entire observable universe. The most direct visual evidence for the existence of supermassive black holes comes from the Black Hole Shadow image, captured by the Event Horizon Telescope. This image showed the silhouette of the central black hole in the galaxy M87, confirming general relativity's prediction for how light behaves in the immediate vicinity of a black hole. This monumental achievement provided a visual representation of the event horizon and the extreme bending of light, marking a significant milestone in astronomical observation. A supermassive black hole is not a perpetual vacuum cleaner that relentlessly sucks up every star and gas cloud. It is actually a highly inefficient consumer. The vast majority of stars in a galaxy are safely orbiting far away from the center, unaffected by the black hole's presence. The black hole only consumes material that loses angular momentum and is nudged close enough to fall into the event horizon. Stars only get pulled in if their orbits are drastically perturbed, usually by a close encounter with another star or a merger event. For the most part, the supermassive black hole sits silently, a quiet, immense anchor to the galaxy. The most active phase in the life of a supermassive black hole is when it powers a quasar in the early universe. This phase lasts for only a relatively short period, a few 100 million years, as the black hole rapidly consumes the abundant gas supplies of the young galaxy. Once the gas supply is exhausted, or the black hole's jets push the remaining fuel away, the quasar activity shuts down, and the black hole enters a quieter dormant phase, which is the current state of most supermassive black holes in the local universe. The event horizon of a supermassive black hole is so large that its surface gravity is actually quite weak compared to a stellar mass black hole. Surface gravity is defined by acceleration, and due to the black hole's mass being spread across a larger radius, the acceleration felt at the boundary is less. This means that if you were floating at the event horizon of a supermassive black hole, you would feel a surprisingly low gravitational pull, far less than that of a stellar black hole, even though the total mass is immensely greater. Dual active galactic nuclei are observed when two supermassive black holes are orbiting each other in the core of a merged or merging galaxy. These dual systems are critical as they are the precursors to the most powerful gravitational wave events. As the two black holes spiral closer, they create intense energy and gravitational ripples. Astronomers detect these systems by observing two distinct energetic cores within a single galaxy, each with its own accretion disk and jets locked in a slow gravitational dance. The gravitational influence of a supermassive black hole extends far beyond its immediate event horizon, affecting the orbital dynamics of stars and gases throughout the galactic bulge. This influence creates a distinct velocity curve in the galactic center, where stars move much faster than expected based on the visible matter alone. Observing these high orbital velocities is one of the key methods used to confirm the existence and precisely measure the mass of a supermassive black hole. The entire galactic core is a silent testament to its immense gravitational presence. Recoil can occur after the merger of two supermassive black holes, potentially ejecting the newly formed larger black hole from the galactic core. If the merger process is asymmetrical, the resulting gravitational waves are emitted preferentially in one direction, imparting a gravitational kick to the merged black hole. This kick can be powerful enough to send the supermassive black hole careening into the galactic halo, or even eject it from the galaxy entirely, creating a rogue supermassive black hole. The presence of an ejected black hole would have profound consequences for the dynamics of the host galaxy's center. We let the quiet power of the supermassive black holes settle gently in our minds. These giants anchor the galaxies, regulating star formation and shaping the universe on the largest scale, silent, immense rulers of the cosmos. As we drift further into the night, we turn our attention toward the missing pieces of the black hole family, the intermediate and primordial singularities. We continue our quiet exploration, turning our minds toward the more elusive members of the black hole family, the intermediate mass black holes and the primordial black holes. These objects, spanning the gap between the stellar mass remnants and the supermassive giants, remain largely hypothetical or difficult to observe, yet they hold key clues to the universe's early history and structure. Let your thoughts soften and your mind remain receptive to these silent, hidden masses. Intermediate mass black holes are a theoretical class of black holes with masses ranging from about 100 to 100,000 times the mass of the Sun. They are the crucial missing link in black hole evolution, as they represent the necessary stepping stone between stellar remnants and supermassive giants. These black holes are too massive to have been formed by the collapse of a single star, yet too small to be classified as supermassive black holes. Their existence would solve the mystery of how supermassive black holes grew so quickly in the early universe by suggesting an abundant source of seed black holes to initiate their rapid growth. One of the primary proposed formation mechanisms for intermediate mass black holes is the runaway collapse of massive stars within dense stellar clusters, such as globular clusters. In these crowded environments, massive stars can rapidly collide and merge, forming a single ultramassive star that then collapses directly into an intermediate mass black hole. Another theory proposes that they form through the continuous merger of smaller stellar mass black holes within the cluster's core, creating a central gravitational sink. This process would happen relatively quickly, providing the necessary large seed masses for the supermassive black holes observed in young quasars. Observational evidence for these intermediate black holes remains scarce, making them a significant mystery. However, strong candidates are found in ultra-luminous X-ray sources that are too bright to be explained by normal stellar mass black holes. These sources are X-ray emitters that are extremely powerful, sometimes suggesting a black hole mass in the intermediate range. Another line of evidence comes from the precise orbital dynamics of stars within the centers of some globular clusters, where a central, unseen mass can be inferred by the motions of the surrounding stars. Primordial black holes are hypothetical black holes that are not formed from the collapse of stars, but are believed to have originated in the first second after the Big Bang. If during that initial rapid expansion, there were minute fluctuations or irregularities in the density of the early universe, some regions of space could have been dense enough to instantly collapse into a black hole under their own gravity. These primordial black holes could theoretically range in mass from extremely tiny, less than a grain of sand, to supermassive. The mass range for primordial black holes is vast, from tiny objects with masses less than a large asteroid to those with hundreds of thousands of solar masses. Primordial black holes with masses smaller than a large asteroid would have already evaporated by now, due to the process of quantum decay. However, those slightly larger could still exist today and could potentially constitute a portion of the universe's mysterious dark matter. If these ancient relics are indeed a component of dark matter, it would resolve one of the most persistent puzzles in cosmology by identifying the unseen mass that shapes the universe. The gravitational microlensing technique is a key method used to quietly search for primordial black holes. When a primordial black hole passes between Earth and a distant star, its gravity can momentarily magnify the star's light. The duration and intensity of this magnification depend on the black hole's mass. Extensive searches using this technique have set strict limits on the abundance of these black holes in the stellar mass and asteroid mass ranges, suggesting they cannot make up the entirety of dark matter, although smaller or larger mass ranges are still possible. Primordial black holes, if they exist, are considered to be purely theoretical objects that would predate the formation of the first stars. They are gravitational fossils, relics of the universe's infancy, formed directly from the primordial soup of the Big Bang. Their properties would be dictated entirely by the conditions of the early universe, offering a unique window into high-energy physics and the moments before the cosmic microwave background was emitted. Their existence would be a profound confirmation of the extreme physics at the quiet dawn of time. The theoretical concept of a substellar mass black hole is also explored, where primordial black holes could have masses as small as the Moon or Earth. These objects are extremely difficult to detect as they do not accrete enough matter to emit X-rays, and their gravitational influence is highly localized. However, if they are numerous, they would collectively exert a significant gravitational presence. The quiet search for these small hidden masses is an active area of research, as their discovery would revolutionize both black hole theory and our understanding of dark matter. Globular clusters. Ancient, densely packed spherical collections of stars are considered the most likely locations to find intermediate mass black holes. The high density of stars in the core of these clusters increases the probability of stellar mergers and collisions, creating a natural environment for their formation. The gravitational influence of an intermediate mass black hole would also help explain the high-velocity dispersion observed in the stars near the core of some globular clusters, providing a key observational signature for their presence. The merger of two intermediate mass black holes would produce a unique gravitational wave signature that is distinguishable from the mergers of stellar mass black holes. This signature, falling into the intermediate frequency range, is a prime target for future space-based gravitational wave detectors. The detection of these mergers would provide definitive proof of their existence and shed light on the initial conditions necessary for the formation of supermassive black holes. The X-ray emissions associated with intermediate mass black holes found in ultra-luminous X-ray sources often display rapid complex variability. The high accretion rate and the strong gravitational pull of the black hole are thought to create unstable flow patterns in the accretion disk, leading to frequent intense flares and shifts in the X-ray spectrum. This energetic behavior is a key observational tool used to distinguish these candidates from normal, less luminous stellar black holes. The X-rays are the flickering bright candle that quietly betrays the presence of the hidden mass. The cosmic microwave background imposes limits on the abundance of primordial black holes. If they were formed too abundantly in the early universe, their gravitational presence would have caused measurable clumping and distortion in the ancient afterglow of the Big Bang. Since the background is observed to be incredibly smooth, this provides strict constraints on the mass and quantity of primordial black holes that could have been formed at that time. The pristine smoothness of the background is a quiet, powerful clue against an overly abundant population of these objects. The theoretical possibility of evaporating primordial black holes gives rise to a potential observational signature. Primordial black holes, with masses smaller than a large asteroid, should be evaporating rapidly today via quantum decay, with the smallest ones exploding in a final burst of gamma rays. Astronomers are actively searching for these final gamma ray bursts, which would provide definitive proof of both these objects and the reality of quantum decay. The quiet search for these micro-explosions is a search for the meeting point of gravity and quantum mechanics. The theoretical maximum mass for a primordial black hole formed in the early universe is bounded by the size of the observable universe at the time of their formation. No black hole could have been larger than the mass contained within the cosmic horizon at the moment of its collapse. This constraint suggests that any supermassive black hole that is primordial in nature must have formed in a specific period known as the radiation-dominated era before the universe began its matter-dominated phase. Tidal disruption events can be used as a quiet probe to search for intermediate mass black holes. When a star is tidally disrupted by such a black hole, the resulting flare of light and X-rays has a unique signature, a specific time evolution and peak luminosity that can be calculated based on the black hole's mass. The observation of events with properties that do not fit stellar mass or supermassive black holes would strongly suggest the involvement of a hidden intermediate black hole. We let the quiet mystery of the intermediate and primordial black holes settle gently in our minds. These elusive objects, the missing links, and the gravitational fossils fill the gaps in our cosmic understanding, hinting at the violent yet efficient processes that drove the universe's evolution. As we drift further into the night, we delve into the physics of these objects, exploring how they warp space and time, giving rise to the concept of gravitational lensing. We now turn our thoughts to the profound physical influence of black holes on the universe around them. Moving beyond their simple mass charge and spin, we explore how they interact with the very stage of existence, space-time itself. Let your body feel as if it is floating in the deepest dark, allowing your mind to comprehend the bending, stretching, and twisting of the invisible fabric that holds everything together in this cosmic tapestry. The existence and properties of black holes are a direct consequence of Albert Einstein's theory of general relativity, which redefines gravity not as a force, but as the curvature of space-time caused by mass and energy. A black hole represents the most extreme possible curvature of this fabric, where the warping becomes infinite at the singularity. It is this profound warping that dictates the paths of all objects, including planets, stars, and light, forcing them to follow the curved geometry of space-time. This is the universal law of motion under extreme gravitational influence. The immense gravity of a black hole acts as a cosmic funhouse mirror through a phenomenon called gravitational lensing. When light from a distant star or galaxy passes near a black hole, its path is bent by the warped space-time, much like light passing through a glass lens. This bending can magnify, distort, or even create multiple ghostly images of the background object, offering an indirect way to detect and study otherwise invisible black holes and their dark gravitational presence. The final image of the black hole's shadow is a direct result of this extreme lensing, where the black hole's immense gravity acts as a perfect silent lens. The distortion of light near the event horizon creates an area of extreme bending known as the light ring. This is a stable circular region where light rays can orbit the black hole in perpetuity. Any light ray entering this zone is effectively trapped, spiraling around the black hole until it either escapes to be seen as a faint, distant image or spirals inward toward the final plunge. The light ring is located just outside the event horizon and is composed of light rays that have circled the black hole at least once, creating the brilliant warped ring of light that defines the black hole's silhouette. The most dramatic effect of a black hole on time is gravitational time dilation, which states that time flows slower near a massive object. The closer you get to a black hole's event horizon, the slower time passes relative to an observer far away. This is not an illusion. It is a physical reality of general relativity. This dilation is so extreme that a fraction of a second near the boundary could equal billions of years in the outside universe. It is a profound, subtle truth. A black hole is not just a destroyer of matter, but a warper of the flow of time itself, creating an immense temporal disparity. The twisting of space-time around a spinning black hole is known as frame dragging, or the lens Thirring effect. This effect means that the rotating black hole drags the very space-time around it into motion, much like a viscous fluid being stirred. This induced motion forces any object or light ray passing through the region to follow the black hole's rotation, regardless of the object's initial velocity. Frame dragging creates a region just outside the event horizon, called the ergosphere, where space-time is forced to rotate faster than the speed of light, making it impossible to remain still relative to a distant observer. The ergosphere is a crucial energetic region existing only around rotating black holes. It is located between the static limit and the event horizon. Within the ergosphere, an object is inevitably dragged along with the rotation of space-time, but it is theoretically possible to extract immense amounts of energy from this region through a process known as the Penrose process. This extraction involves launching a particle into the ergosphere in such a way that its negative energy part falls into the black hole, while its positive energy part escapes effectively, harvesting the rotational energy of the black hole. The gravitational potential near a black hole is so immense that it is the most efficient energy conversion mechanism in the known universe. Matter falling into the black hole's gravity well converts potential energy into kinetic energy. Friction in the accretion disk then converts this kinetic energy into thermal energy, which is radiated as light. This process can convert up to 42% of the infalling matter's rest mass into energy far exceeding the efficiency of nuclear fusion. This transformation is why quasars are so luminous. They are quietly and efficiently converting gravitational potential into blinding light. The Schwarzschild solution is the mathematical solution to Einstein's field equations that describes the space-time geometry around a non-rotating, uncharged spherical mass. It provides the precise mathematical description of the event horizon and the singularity for the simplest type of black hole. The Schwarzschild radius, the formula defining the size of the boundary, is derived directly from this solution, providing the foundational definition for black hole size based purely on mass. The Kerr solution is the more complex mathematical solution that describes the space-time geometry around a rotating, uncharged mass. It accounts for the effects of angular momentum, including the oblate event horizon, the ergosphere, and the ring singularity. The Kerr solution is the most important solution for describing real-world black holes, as the precursor stars that form them are almost always rotating. This solution confirmed that a black hole's gravity dictates the warping of space, while its rotation adds a subtle yet powerful twisting motion. Gravitational waves are ripples in the fabric of space-time itself, generated by the acceleration of immense masses such as the merger of two black holes. These waves travel at the speed of light, stretching and squeezing space-time as they pass. The detection of these waves provided the most direct evidence that black holes exist, and that space-time behaves exactly as predicted by general relativity under extreme gravitational stress. The quiet passage of these waves through the cosmos is the universe's ultimate confirmation of Einstein's genius. The warping of space-time means that an astronaut falling toward a black hole would see the entire visible universe compress into a tiny, intensely bright spot above their head. As the astronaut approaches the photon sphere, the light from distant galaxies that would normally arrive from all directions is bent and focused by the black hole's gravity. The extreme gravitational lensing creates a visual distortion where all the light from the outside cosmos is funneled into a small, super intense region directly opposite the black hole. The final view, before crossing the horizon, is of the entire universe compressed into a single, blinding point. The theoretical Penrose process is a thought experiment demonstrating how energy can be extracted from a black hole's rotation. It suggests that by dropping a particle into the ergosphere and having it split in two, the fragment with negative energy falls into the black hole, while the remaining fragment escapes with more energy than the initial particle. This process harvests the black hole's rotational energy, causing the black hole to slowly decrease its spin. While the Penrose process is purely theoretical, it highlights the immense energy reservoir stored within the angular momentum of rotating black holes. The holographic principle is a radical concept deeply linked to black hole entropy, suggesting that the information defining a three-dimensional volume of space can be entirely encoded on its two-dimensional boundary. This idea originated from the theory that a black hole's entropy is proportional to the area of its event horizon, not its volume. Extended to the universe, the principle suggests that all the reality we experience might be a massive holographic projection with the information encoded on a distant cosmic horizon. The event horizon is thus seen not just as a boundary, but as a subtle, quiet screen holding the entire universe's data. The extreme curvature of space-time means that the concept of inside a black hole is relative. Once the event horizon is crossed, the dimension of time and the radial dimension of space effectively swap roles. The radial direction pointing toward the singularity becomes the time-like dimension, the inescapable future, while the former time dimension becomes a space-like dimension. This geometric swap is why all paths lead inward. Mathematically, the singularity is simply the only possible future. This is the profound reordering of reality that dictates the destiny of everything that falls in. The entire study of black hole space-time geometry relies on the fundamental assumption that gravity is always attractive. This assumption, derived from Einstein's equations, ensures that space-time warps inward toward the mass, creating the absolute trap of the black hole. The only known exception to this is the repulsive effect of dark energy on the largest intergalactic scales, which is an entirely separate cosmic phenomenon. On the local scale of the black hole, the massive density guarantees that the warping of space-time is overwhelmingly inward, and gravitational dominance is absolute. We let the quiet, profound geometry of space-time and gravity settle gently in our minds. The bending of light, the slowing of time, the twisting of space. These are the subtle yet absolute effects of the black hole's presence, the core principles that define its mystery. As we drift further into the night, we delve into the quantum mechanics of these objects, exploring how they can theoretically emit energy and slowly evaporate, revealing a quiet light within the ultimate darkness. We shift our focus now from the massive classical gravity of black holes to the subtle quantum forces at play on the event horizon. This is the realm of Stephen Hawking's greatest theoretical work, where the ultimate darkness reveals a quiet long-term light. Let your mind feel weightless and your thoughts soft as we explore the quantum decay of the black hole, a process that promises their eventual distant end. The faint thermal radiation that is predicted to be emitted by black holes due to quantum effects near the event horizon is known as quantum decay. Contrary to the classical notion that nothing can escape a black hole theory, proposes that quantum fluctuations cause pairs of virtual particles, a particle and an antiparticle, to constantly pop into existence near the horizon. When this happens, one particle may fall into the black hole, while the other escapes to be detected as thermal radiation. The energy for this escaping particle comes from the black hole's mass, causing the black hole to slowly lose mass over time. The emission of this radiation means that black holes are not truly black in the absolute sense, but instead glow faintly with a black-body spectrum related to their temperature. The black hole's temperature is inversely proportional to its mass, meaning smaller black holes are hotter and evaporate faster, while larger supermassive black holes are incredibly cold and evaporate over unimaginably long timescales. The light emitted is extremely low energy and virtually impossible to detect from stellar mass or supermassive black holes because it is overwhelmed by the heat of the cosmic microwave background. The theoretical maximum lifespan for a supermassive black hole is estimated to be over 1, followed by 100 zeros years, a staggering number far longer than the current age of the universe. The slow rate of mass loss via this quantum emission means that only the smallest primordial black holes, with masses less than a large asteroid, would be evaporating and potentially exploding today. The largest black holes will persist silently consuming the universe long after the last stars and planets have faded. The concept of quantum decay links the black hole's mass to its temperature and its entropy. The black hole's mass is the source of the energy, its temperature dictates the rate of radiation, and its entropy is the measure of the information stored on the event horizon. The inverse relationship between mass and temperature is crucial. The hottest objects in the universe are the smallest, lightest black holes, while the most massive are the coldest. This is a profoundly counterintuitive concept in thermodynamics. The evaporation of a black hole eventually leads to its complete disappearance in a final massive gamma-ray burst. As a black hole loses mass through quantum decay, its temperature increases exponentially, accelerating the evaporation rate. The smallest remaining fraction of the black hole evaporates extremely quickly in a final explosive burst of high-energy gamma rays. Scientists are actively searching for these gamma-ray signatures, which would provide the ultimate confirmation of this theoretical process and the existence of primordial black holes. The process of evaporation is the cornerstone of the black hole information paradox, one of the most fundamental, unsolved problems in modern physics. The paradox lies in the conflict between general relativity's apparent erasure of information and quantum mechanics' absolute law that information cannot be truly destroyed. If the black hole simply evaporates, where does the stored information go? The resolution of this paradox is expected to require a full complete theory of quantum gravity. The idea that information might be encoded on the event horizon led to the theoretical concept of fuzzballs. This radical theory suggests that the singularity and the event horizon might be replaced by a diffuse, dense object made of quantum strings without a sharp, classical horizon. In this model, there is no loss of information, as all the information about the black hole's contents is contained in the quantum state of the fuzzball's surface. This is one of the many theoretical attempts to resolve the information paradox without violating the core principles of quantum mechanics. The gravitational field of a black hole is not strong enough to create this quantum decay alone. It requires the presence of the quantum vacuum. The energy for the emitted particles does not come directly from the black hole's gravity, but from the conversion of the energy stored in the negative half of the virtual particle pair that falls into the black hole. The black hole acts as a catalyst, using its extreme gravitational gradient to separate the virtual pair and ensure that one particle carries away positive energy. The entropy of a black hole is proportional to its surface area, not its volume. This counterintuitive fact implies that the information stored in a black hole is related to the two-dimensional surface of the event horizon rather than the three-dimensional volume within it. This relationship is crucial to the formulation of the holographic principle, suggesting a deep connection between the geometry of space-time and the flow of information in the universe. The vast empty space within a black hole holds less information than its skin. The search for primordial black hole explosions is conducted using gamma-ray telescopes. Astronomers look for sudden, extremely high-energy bursts of gamma rays that have the unique signature of a final rapid evaporation. While no definitive explosion has been detected, the continued search provides increasingly tight constraints on the maximum abundance of these ancient objects in the universe today. The non-detection of these bursts helps refine models of the early universe. This quantum emission implies that a black hole can only grow in mass if it consumes matter faster than it evaporates. In the current universe, even stellar mass black holes are so cold that the energy they emit is overwhelmed by the energy they absorb from the cosmic microwave background. Therefore, all known black holes are currently growing very slowly. Only in the far future, when the background radiation has cooled significantly, will evaporation become the dominant process for the largest black holes. The final explosion of a primordial black hole, although immense in energy, is very short-lived, lasting only a tiny fraction of a second. The mass loss accelerates so quickly in the final moments that the explosion is virtually instantaneous. This makes the detection of these events extremely challenging, requiring continuous monitoring of the gamma-ray sky to catch the fleeting final flash of these ancient relics of the Big Bang. The theoretical firewall paradox is a refinement of the information paradox that suggests that the event horizon must be replaced by a wall of high-energy particles to prevent the violation of quantum mechanics. This hypothetical firewall would instantly incinerate anything that falls toward it, resolving the information paradox, but violating Einstein's principle that the experience of crossing the horizon should be smooth and seamless. This paradox remains a critical point of theoretical contention among physicists. The maximum energy released by a black hole's evaporation in its final moments is equivalent to converting its entire remaining mass into energy via the famous mass-energy equivalence formula. Although the final mass is infinitesimal, the resulting energy burst is immensely powerful, similar to a small localized supernova, but powered by quantum decay rather than fusion. This is the ultimate final act of the black hole marking its irreversible transition from existence to nothingness. We let the quiet quantum reality of this emission and black hole evaporation settle gently in our minds. The idea that even the most absolute gravitational prisons will eventually fade, dissipating their mass back into the universe over unimaginable timescales, is a profound and gentle truth. The deepest dark is temporary, and even it must eventually yield to the gentle, persistent light of quantum mechanics. As we drift further into the night, we delve into the most violent events associated with black holes, their collisions, and the immense gravitational ripples they send through space. We shift our focus now to the ultimate cosmic cataclysms, the collision of black holes, and the detection of the space-time ripples they unleash. These events are the most energetic in the universe, transforming silence into a measurable wave in the very fabric of existence. Let your mind feel vast and expansive as we explore the physics of these cosmic echoes. Space-time ripples are disturbances in the geometry of space-time itself, generated by the acceleration of massive objects. They were first predicted by Albert Einstein a century ago as a consequence of general relativity. When two black holes orbit each other, they constantly accelerate, generating these waves. The waves travel outward at the speed of light, carrying immense energy away from the orbiting system. When they pass through a region of space, they temporarily stretch and squeeze space, a distortion so subtle it is almost impossible to measure without specialized instruments. The first direct detection of these space-time ripples occurred in 2015 by the Laser Interferometer Gravitational Wave Observatory. This signal was generated by the merger of two stellar mass black holes, 36 and 29 times the mass of the Sun, into a single 62 solar mass black hole. The missing mass, about 3 solar masses, was converted entirely into the energy of the space-time ripples in a fraction of a second. This event confirmed Einstein's prediction and heralded the dawn of a new field of astronomy. The process of a black hole merger is characterized by 3 distinct phases: in-spiral, merger, and ring-down. During the in-spiral phase, the two black holes orbit each other, emitting waves that gradually shrink their orbit. During the merger phase, the two event horizons touch and combine into a single, larger black hole. Finally, the ring-down phase occurs as the newly formed black hole settles into its final stable configuration, emitting a final burst of characteristic waves that gradually fade. The entire process for stellar mass black holes takes only a matter of seconds. The frequency of the space-time ripples increases as the black holes spiral closer, creating a characteristic chirp sound in the detectors. As the black holes accelerate and their orbital period shortens, the frequency and amplitude of the emitted waves increase. This rise in frequency, culminating in the loudest signal just before the merger, is what creates the chirp that is analyzed by astronomers. The duration and frequency of this chirp encode the precise mass spin and orbital parameters of the merging black holes. Detectors like the Laser Interferometer Gravitational Wave Observatory work by using laser interferometry to measure minute changes in distance. The detectors consist of 2 long arms, typically 4 kilometers in length at a precise right angle. A laser beam is split and sent down each arm, then reflected back to the source. A passing wave stretches one arm while squeezing the other, causing a tiny mismatch in the laser light's return time. This microscopic difference, less than 1,000th the diameter of a proton, is the quiet signal of a space-time ripple. The merger of two supermassive black holes would generate space-time ripples with periods that are far too long to be detected by ground-based detectors. Instead, these ultra-low frequency waves are the target of future space-based missions, or by observing tiny shifts in the precise timing of radio signals from an array of millisecond pulsars. The immense power of these mergers means their gravitational ripples would dominate the gravitational landscape of the entire cosmos. The energy released during a stellar mass black hole merger is so immense that it temporarily makes the system brighter than all the stars in the universe combined, but only in these gravitational waves. In the final fraction of a second before the first detected merger, the power output in these waves was estimated to be 50 times greater than the total electromagnetic energy output of the entire visible universe. This highlights the extreme efficiency of converting mass into energy through gravitational wave emission. The gravitational wave signals provide a method for measuring cosmic distances independent of the electromagnetic distance ladder. The intrinsic power of the gravitational wave signal can be precisely calculated from the waveform. By comparing this intrinsic power with the amplitude measured on Earth, astronomers can determine the precise distance to the merger. These standard sirens provide a new powerful tool for measuring the expansion rate in the fundamental scale of the universe. The detection of black holes with masses in the mass gap, the theoretical range between 45 and 135 solar masses, was entirely a result of gravitational wave astronomy. These black holes, which were not expected to form from single-star collapse, are now confirmed to exist through merger events. The discovery suggests that black holes in this mass range are either formed through a hierarchical process, where smaller black holes merge to create a mass gap black hole, or that the theory of stellar death needs fundamental revision. The final black hole, created by a merger, is always more massive than the two initial black holes combined, but its area is also always greater than the sum of the areas of the two initial black holes. This is a restatement of the second law of black hole thermodynamics, which dictates that the total event horizon area can never decrease. The merging black holes emit mass as gravitational waves, but the resulting single black hole always has a larger surface area, reflecting the increased entropy of the combined system. The spin of the black holes is conserved during the merger, but the final spin of the resulting black hole is influenced by the initial spins and the angle of the collision. The spin of the initial black holes and the alignment of their axes determine how much gravitational energy is emitted, and the final rotation rate of the merged black hole. Gravitational wave analysis is the only method by which the spin of these compact objects can be directly measured with high precision. A merger of two black holes can impart a recoil or gravitational kick to the final black hole. If the emission of gravitational waves during the final ring-down phase is asymmetrical, the waves will carry more momentum in one direction, causing the resulting black hole to be kicked in the opposite direction. These kicks can be immensely powerful, potentially ejecting the new black hole from its host cluster, or even from its galaxy entirely. The observation of such a recoiling black hole would be a major astronomical find. The detection of the first binary neutron-star merger was a crucial milestone, as it also generated a simultaneous electromagnetic signal known as a kilonova. This multi-messenger astronomy confirmed the source of short gamma-ray bursts, provided an origin for the universe's heaviest elements, and offered a powerful cross-check on the gravitational wave signal, setting a new standard for cosmic observation. Gravitational wave events are extremely frequent in the universe. While the observatories only detect a handful of merger events within their sensitive range per year, the total number of black hole and neutron star mergers across the cosmos is estimated to be incredibly high. The space-time around us is constantly being stretched and squeezed by the subtle, continuous background hum of these mergers occurring in distant galaxies. The universe is in effect constantly rippling with the echoes of ancient collisions. The gravitational wave signal effectively stops when the event horizons touch, as the merger creates a new single black hole, while the strongest part of the signal is the final plunge before the horizons meet. The formation of the new event horizon essentially seals the system. The final part of the signal, the ring down, is the settling of the new black hole into its stable form. This final transition marks the end of the two-body problem and the beginning of the new larger single singularity. We let the quiet, profound power of black hole mergers and the subtle ripple of gravitational waves settle gently in our minds. These silent cosmic echoes are the most direct language of extreme gravity, linking the death of stars to the stretching of space itself. As we drift further into the night, we turn our attention toward the practical methods astronomers use to find these invisible gravitational prisons. Part 11. Hunting the Invisible. We have explored the physics and the extreme nature of black holes. Now, we quietly turn our minds to the observational challenge. How do astronomers actually find an object that is by its very definition completely invisible? Let your focus soften as we explore the indirect clues, the telltale signs, and the silent gravitational signatures that betray the presence of a black hole in the vastness of space. The primary method for finding active stellar mass black holes is by detecting their X-ray emissions. Black holes are often found in binary systems with companion stars. As the black hole accretes gas from its companion, the material spirals inward in an accretion disk, heating up to millions of degrees before crossing the event horizon. This extreme heat causes the inner disk to emit intense X-rays, which orbiting telescopes can detect. The irregular flickering and high energy of this X-ray light is a clear dinner bell that announces the presence of a compact feeding object. Supermassive black holes are often detected by observing the extreme orbital velocities of stars in the galactic core. Since the stars orbit a central unseen point of mass, astronomers can use the speed of the stars, particularly the innermost S-stars, to calculate the mass of the invisible object. If the calculated mass is too great to be explained by a cluster of normal stars or a concentration of dark matter, the only remaining explanation is a supermassive black hole. The precise elliptical orbits of these S-stars are the most convincing gravitational evidence. Tidal disruption events provide a rare, spectacular means of finding otherwise dormant black holes. When a star is torn apart by a black hole's gravity, the resulting flare of light from the rapidly accreting stellar debris can last for weeks or months. This is a transient event, a brief, blinding flash that betrays the black hole's location. Astronomers constantly scan the sky for these sudden high-energy flares, which act as a powerful confirmation of a quiet black hole's presence in a seemingly normal galaxy. The detection of a black hole's shadow is the most direct visual evidence achieved by the Event Horizon Telescope. This virtual Earth-sized telescope is formed by linking radio observatories across the globe. This immense resolution allows astronomers to image the silhouette of the event horizon cast against the background of the glowing accretion disk. The shadow's size and perfect circularity are key observational proofs predicted by general relativity. Gravitational lensing is used to find black holes and other compact objects through the bending of light. Although strong lensing is often used to find massive galaxy clusters, microlensing is a technique that can find individual, isolated stellar mass or primordial black holes. As a black hole passes in front of a distant star, its gravity momentarily magnifies and brightens the star's light. The duration of this subtle brightening event provides clues about the mass of the unseen lensing object. Gravitational waves offer an entirely new method of detection that is independent of light. The Laser Interferometer, Gravitational Wave Observatory, and its partners detect the ripples in space-time caused by the merger of two black holes. The frequency and amplitude of the chirp signal confirm the object's identity as black holes and precisely measure their masses and spins. This method is the most direct and least ambiguous way to confirm a black hole's presence and properties, allowing us to hear the cosmos. The search for primordial black holes relies on detecting the final bursts of gamma rays from their theoretical evaporation via quantum decay. If these black holes with masses in the asteroid range exist, they would be evaporating and exploding today in a powerful, short-lived gamma-ray flash. Gamma-ray space telescopes are used to continuously scan the sky, searching for the unique spectral signature of these quantum decay events. The presence of relativistic jets and radio lobes is a clear signature of an actively feeding supermassive black hole. The powerful jets of plasma launch from the black hole's poles, and the massive radio-emitting bubbles they inflate in the intergalactic medium can be observed across vast distances by radio telescopes. These radio signatures are often the first hint that a distant galaxy harbors a powerful, active galactic nucleus at its core. Infrared observations of the galactic center are crucial for studying our own central black hole, because interstellar dust and gases obscure visible light. The intense dust clouds in the galactic core block nearly all visible and X-ray light, but infrared radiation can penetrate this veil. Infrared telescopes allow astronomers to track the orbits of the stars closest to the black hole, providing the necessary data for mass calculations. The detection of high-energy particles, such as neutrinos and cosmic rays, can sometimes be linked to black hole activity. While still a developing field, some ultra-high-energy neutrinos have been traced back to active galactic nuclei, suggesting that black holes are powerful accelerators of these particles. Multi-messenger astronomy, combining gravitational waves, electromagnetic signals, and particle detections, is the future of black hole hunting. Iron X-ray spectral lines in the X-ray spectrum are used to measure the spin of a black hole. Gas spiraling into the accretion disk emits X-rays with a distinct spectral signature. The extreme gravity and warping of space-time near the black hole distort and broaden this line. By precisely measuring the distortion, astronomers can calculate the velocity of the inner disk, which in turn reveals the black hole's rotation rate. Quasars and active galactic nuclei are used as cosmic lighthouses to probe the gas clouds and structure of the early universe. The immense light emitted by the accretion disk of a distant black hole shines through intervening gas clouds. The gas absorbs light at specific wavelengths, creating absorption lines in the quasar's spectrum. Analyzing these absorption lines reveals the composition, temperature, and motion of the gas clouds that existed billions of years ago. The search for intermediate mass black holes relies on finding them in globular clusters through dynamic analysis. By modeling the gravitational influence required to explain the motions of stars within these dense ancient clusters, astronomers can infer the mass of an unseen central black hole, even if it is not actively accreting matter. The absorption of X-rays from a binary companion is sometimes the only clue of a black hole's presence. In some high-mass X-ray binaries, the black hole's accretion disk is viewed edge-on, meaning the bright X-rays are blocked by the disk itself. However, the X-rays are still emitted at certain angles, or the companion star shows signs of being stripped of material, indicating the presence of a compact object whose mass can be calculated. The future of black hole detection involves space-based gravitational wave observatories. These future detectors will be sensitive to the much lower frequency gravitational waves produced by the merger of supermassive black holes in the cores of merging galaxies. This will allow astronomers to witness the most energetic events in the universe and track the growth of these galactic anchors across cosmic time. We let the quiet, persistent effort of hunting the unseen black holes settle gently in our minds. The universe is full of invisible things, but through ingenuity and the subtle clues of gravity and light, humanity has learned to map the location and measure the properties of these ultimate gravitational prisons. As we drift further into the night, we explore the immense and profound role that these black holes play in the evolution of the entire cosmos. We drift now from the technical challenge of black hole hunting to the immense sprawling canvas of their influence across the universe. Black holes are not isolated cosmic entities. They are the architects of galaxies, quietly shaping the evolution, star formation, and destiny of the entire cosmic web. Let your mind feel anchored and vast as we explore the coevolution of the black hole and its host galaxy. The most profound realization of modern cosmology is that supermassive black holes and their host galaxies co-evolve. The mass of the central black hole is found to be proportional to the mass of the galaxy's central bulge, a relationship known as the mass-velocity dispersion relation. This universal correlation suggests that the growth of the black hole and the growth of the galaxy are deeply intertwined, with processes in one affecting the other. The black hole is thought to be a self-regulator, preventing the galaxy from growing too large too quickly. The primary mechanism by which these black holes influence their galaxies is through active galactic nuclei feedback. When the black hole actively feeds its accretion disk, emits powerful winds and relativistic jets. This energetic outflow interacts with the surrounding gas clouds, heating them up or pushing them out of the galaxy. This action prevents the gas from cooling down to form new stars, effectively shutting down star formation in the galaxy's center and bulge. The feedback mechanism is crucial to explaining the existence of red and dead elliptical galaxies. These massive galaxies have exhausted their gas supply and no longer form new stars. The current theory suggests that the supermassive black hole in these galaxies was extremely active in the past, operating in its quasar phase, which provided enough powerful feedback to clear out the galaxy's star-forming fuel. This explains the transition from gas-rich star-forming spiral galaxies to quiet gaseous poor elliptical galaxies over cosmic time. The jets from a black hole can also sometimes trigger star formation in some circumstances. As the powerful jets sweep through the gas, they can compress the gas clouds at their boundaries. This compression can sometimes initiate the gravitational collapse of the clouds, leading to bursts of star formation at the edge of the active nucleus's influence. This dual role, shutting down star formation in the center while occasionally triggering it at the edges, highlights the complex and nuanced influence of the central black hole. Galactic mergers are the primary mechanism for feeding the supermassive black holes in the late universe. When two galaxies collide and merge, the gravitational disruption shuffles gas and dust into the newly formed galactic core. This abundance of fresh fuel ignites the central black hole, causing it to enter a brief active phase as an active nucleus. The resulting energetic feedback from the active nucleus then helps clear the core of the remaining gases, finalizing the merger and leading to a quiet, fully formed elliptical galaxy. The event, horizon of a supermassive black hole, is the only thing in the universe that can be measured directly to infer the properties of the host galaxy. The size and shape of the black hole's shadow are direct visual representations of its mass and spin. These black hole properties, in turn, are tightly linked to the galaxy's properties via the mass-velocity dispersion relation, allowing astronomers to use the black hole itself as a standard ruler for measuring the dynamics of the galactic center. The gravity of the supermassive black hole is not uniform across the galaxy, meaning it influences different regions in distinct ways. The influence is dominant in the immediate vicinity of the event horizon, where it dictates the orbits of the innermost stars. Farther out in the galactic bulge, its influence is significant in setting the velocity dispersion of the stars. In the galactic disk, however, the black hole's gravity is negligible compared to the collective gravity of the dark matter and the billions of stars. The black hole's spin is thought to be crucial for determining whether it launches powerful continuous relativistic jets. Black holes with high spins are theorized to have the necessary energetic and magnetic field structure to launch persistent jets, leading to the formation of radio galaxies. Conversely, black holes with lower spins often only produce winds or transient flares, explaining the diversity of active galactic nuclei types observed in the universe. The mass of the central black hole can regulate the dispersion of stellar velocities in the galactic bulge. The greater the black hole's mass, the greater the gravitational influence on the stars orbiting close to it, causing them to move at higher, more randomized velocities. This direct correlation is the most robust observational evidence for the co-evolution of black holes and galaxies. The immense gravity of the supermassive black hole creates a sphere of influence within the galactic core. This is the region where the gravitational pull of the black hole dominates the gravitational pull of the surrounding stars and gas. For our own Milky Way's black hole, this sphere extends roughly 10 light-years from the center. Inside this sphere, the dynamics are entirely governed by the black hole, while outside the collective mass of the stars takes over. The growth of supermassive black holes is intimately tied to the availability of cold gas. In the early universe, cold gas was abundant, allowing black holes to feed rapidly and become quasars. As the universe aged, gas became hotter and scarcer, limiting the black hole's food supply and transitioning them into their current, quieter state. Galactic mergers are necessary to violently funnel new supplies of cold gas back into the core, reigniting the activity. The presence of a supermassive black hole prevents runaway star formation in the galactic core. If the black hole were not there to regulate the gas supply through feedback, the immense density of gas in the core would lead to rapid, unsustainable star formation, which would quickly exhaust all the available fuel and potentially destroy the galactic core. The black hole acts as an essential, although violent regulator for the stability of the galaxy. The alignment of a black hole's spin is often aligned with the angular momentum of the host galaxy. This alignment is expected in galaxies that have grown slowly through continuous, smooth accretion of gas from the surrounding disk. Conversely, black holes whose spin is misaligned with the galaxy's disk are often found in galaxies that have recently undergone a violent merger, which has randomly changed the direction of the angular momentum. The jets from an active nucleus can enrich the intergalactic medium with heavy elements. As the powerful jets push matter out of the galaxy, they carry with them gas that has been enriched by heavy elements from supernova explosions. This expelled material then mixes into the intergalactic medium, providing the fuel for future star and galaxy formation elsewhere. This process shows that the influence of the black hole extends far beyond its host galaxy, acting as a crucial element in the cosmic chemical cycle. The final merger of two supermassive black holes provides the necessary gravitational catalyst for the host galaxy to truly settle into its final stable form. The intense gravitational waves and the recoil kick from the final merger help clear the core of any remaining gas and stellar debris, ensuring that the merged elliptical galaxy is completely dormant and stable. This final most powerful event marks the quiet completion of the galaxy building process. We let the quiet, profound co-evolution of black holes and galaxies settle gently in our minds. These silent giants are not just destroyers. They are the necessary violent anchors that regulate growth-shaped morphology and dictate the ultimate destiny of the galaxies they inhabit. As we drift further into the night, we explore the long-term future of these objects and their ultimate fate in the dark, cold universe. We now drift our thoughts toward the unimaginable expanse of cosmic time, exploring the fate of black holes and the universe in the far, far future. Time on this scale stretches beyond human comprehension, measured in a 1 followed by many zeros. Let your mind feel vast and timeless as we contemplate the slow, quiet decay of existence. In the near cosmic future, all known black holes are currently growing because they are consuming more mass than they are losing through quantum decay. Even though this quantum emission is constantly being emitted, the energy absorbed by the black hole from the omnipresent cosmic microwave background is greater. This means that for the next few 100 billion years, every black hole in the universe is gaining mass, albeit very slowly, making them more massive and slightly colder over time. The process of quantum decay will eventually lead to the complete evaporation of all black holes, but this will only begin in the far future, known as the degenerate era. This era begins when the last stars in the universe have exhausted their fuel and faded to black, leaving behind a cosmos populated only by white dwarfs, neutron stars, planets, and black holes. At this point, the cosmic microwave background will have cooled sufficiently for the black hole's temperature to exceed it, allowing evaporation to become the dominant net mass-losing process. The smallest stellar mass black holes will take approximately a 1, followed by 67 zeros years to fully evaporate. This staggering timescale is vastly longer than the time it takes for the protons that make up all normal matter to decay. Therefore, the longest-lived objects in the universe are not stars or planets, but black holes. Their immense mass and slow decay rate make them the silent inheritors of the universe's matter, the last structures standing. The largest supermassive black holes will take even longer, with evaporation timescales reaching a 1 followed by 100 zeros years, a figure that effectively means they are almost eternal on any human timescale. They will outlive every star, every planet, and every other compact object. These black holes will become the final structures of the universe, consuming the last scattered particles and remaining matter before they too finally fade into a brief, blinding flash of pure energy. The period of maximum black hole activity is known as the black hole era, which begins after the evaporation of the last normal matter and continues until the final black holes evaporate. During this era, the universe is virtually empty, with only these massive gravitational prisons remaining. The black holes will occasionally consume the scattered debris of dead stars growing slowly, but the overall trend will be one of net mass loss via quantum decay. The eventual fate of the universe linked to black hole evaporation is a state known as heat death. This final stage is reached when all energy is uniformly distributed and the universe is characterized by a maximal state of entropy. The final remnants of the black hole evaporation process will be a cold, ultra-thin gas of photons and fundamental particles with no temperature variations to drive any process. The universe will become dark, quiet, and completely featureless. Before the evaporation of black holes begins in earnest, the universe must first undergo the decay of all normal matter. According to current theories of particle physics, protons will eventually decay, transforming all atoms into radiation and neutrinos over a timescale of about 1, followed by 34 zeros years. This process will strip all planets, white dwarfs, and remaining structures into their fundamental components, leaving behind only the black holes and a thin soup of elementary particles. The gravitational influence of supermassive black holes will eventually cause the ejection of stars and remnants from the galactic core. Through a process of gravitational scattering, the black hole will randomly scatter the remaining stellar remnants and debris. Some remnants will be flung into the intergalactic void, while others will be nudged into the black hole. Over unimaginable eons, the galactic core will be slowly emptied of all its stars. The theoretical concept of a white hole is often considered as the time-reversed solution to the black hole equations. A white hole would be a region of space-time that matter can only escape from, and nothing can enter. Mathematically, it is the exact opposite of a black hole. While there is no physical evidence for their existence, the mathematics is sound. White holes, if they existed, would be an explosive generative counterpart to the black hole's consumption. The final moment of a black hole's evaporation is a violent, immensely energetic event. The smallest remaining mass evaporates instantly in a burst of gamma rays. This final flash is the ultimate irreversible conversion of mass into energy, marking the end of the black hole's existence and the final release of all the information and energy it had contained over cosmic time. The universe will be too large and diluted for the matter from black hole evaporation to initiate new star formation. By the time the black holes begin to evaporate in the degenerate era, the universe will have expanded so significantly that the remaining particles will be too sparse to ever coalesce. Therefore, the final matter released by black holes will simply join the ultra-thin, cold uniform gas of the heat-death universe, incapable of forming any new structure. The theoretical possibility of wormholes is often discussed in the context of rotating black holes. While mathematically permitted by the equations, a wormhole would need to be threaded with exotic matter, possessing negative energy density to remain stable and traversable. The immense difficulty and theoretical instability make the existence of traversable wormholes highly unlikely. But the concept remains a tantalizing quiet bridge between different regions of space-time. The maximum mass of a black hole is not theoretically limited, provided there is enough matter available to sustain its growth. However, in the observable universe, the largest known black holes are in the tens of billions of solar masses. Their size is ultimately limited by the amount of matter and the time available in the universe to consume it. The ultimate end of the universe is uncertain, depending on the nature of dark energy. If dark energy continues to accelerate the universe's expansion, the cosmos will end in a state of heat death. If dark energy increases in power, it could lead to a big rip, tearing apart galaxies, stars, and eventually atoms. The fate of black holes is therefore contingent on the ultimate destiny of the space-time they inhabit. The entire journey into the extreme future is a quiet, profound meditation on entropy, the relentless progression toward disorder and uniformity. Black holes are the ultimate storage for maximum entropy, and their evaporation is the final grand act that pushes the universe toward its eventual cold and quiet resting place. We let the quiet, vast stillness of the extreme future settle gently in our minds. The fate of the black holes, the slow decay of matter, the relentless pursuit of heat, death. These are the final, absolute truths of the cosmos, a journey toward ultimate stillness. As we drift further into the night, we explore the quiet philosophical questions that these cosmic monoliths impose upon our understanding of reality. We have traversed the vast physics and the unimaginable timescales of black holes. Now, we arrive at the quietest questions, the mysteries that have resisted decades of research, forcing us to stand at the very edge of our understanding. Let your mind feel unburdened and open to the deepest, most persistent puzzles these cosmic monoliths present. The most profound mystery is the resolution of the black hole information paradox. The conflict between general relativity's erasure of information and quantum mechanics' absolute preservation of information remains unsolved. The question of whether information is truly destroyed or merely inaccessible is a fundamental puzzle that is expected to require a unified theory of quantum gravity to resolve. The paradox is the quiet signpost pointing toward the next great revolution in physics, compelling a deeper understanding of reality. The mystery of the black hole singularity remains despite the mathematical certainty of general relativity. Since the singularity is defined by infinite density and curvature, it represents a breakdown in our physical laws. The quiet expectation is that a theory of quantum gravity will replace the singularity with a finite, physically meaningful region, perhaps a ball of quantum foam, or the heart of a fuzzball, thus resolving the issue of infinity and providing a complete picture of the black hole's core. The rapid growth of supermassive black holes in the early universe remains an unsolved mystery. The discovery of immensely massive quasars only a few 100 million years after the Big Bang suggests an extraordinarily efficient growth mechanism that cannot be fully explained by simple accretion or mergers alone. The question of the seed, black holes, how they formed, and what their initial masses were, is crucial to understanding the efficient, rapid evolution of the entire cosmic web. The nature of dark matter is deeply linked to the possibility of primordial black holes. If these black holes formed in the first moments of the Big Bang exist in the asteroid mass range, they could constitute the invisible dark matter that makes up 85% of the universe's mass. While gravitational experiments have largely constrained this possibility for most mass ranges, the quiet search for these invisible, primordial black holes continues, offering a potentially elegant yet elusive solution to the dark matter puzzle. The theoretical possibility of traversable wormholes remains a persistent mystery. While the mathematics allows for the existence of wormholes, bridges connecting two different regions of space-time, they would be inherently unstable and require the presence of exotic matter with negative energy density to keep their throat open. Whether such matter exists in nature, or whether the wormhole could be created under extreme gravitational stress, remains a mystery confined to the realm of theoretical physics and thought experiments. The existence of the intermediate mass black holes, the missing link between stellar and supermassive black holes, remains unconfirmed. Their existence is necessary to explain the rapid growth of the supermassive ones, but definitive, unambiguous observations of them are rare. The quiet search for these intermediate black holes in dense environments, like globular clusters, or through unique gravitational wave signatures, continues to fill the gap in our understanding of black hole evolution. The question of whether the event horizon is truly smooth and featureless is still debated. While general relativity predicts a perfect spherical horizon, quantum theories and the paradox of the firewall suggest that the horizon might be a highly energetic, complex, quantum-entangled surface. The answer to this mystery would determine whether a traveler would experience a smooth crossing or instantaneous incineration, profoundly affecting the physics of the boundary. The origin of the immense power required to launch relativistic jets from a black hole remains only partially understood. The jets are believed to be powered by the magnetic field lines threaded through the accretion disk, converting the black hole's rotational energy into kinetic energy. However, the exact mechanism for collimating this plasma into a tight beam and accelerating it to near the speed of light remains a complex, unsolved problem in plasma physics and general relativity. The gravitational interaction between a black hole and the quantum vacuum is a profound mystery. The theoretical emission of quantum radiation requires the quantum vacuum near the horizon to be energized by the black hole's gravitational field. The exact mechanism by which a classical object interacts with quantum fields to produce thermal radiation is a complex problem that requires deeper understanding of the interplay between the two foundational theories of physics: the mass-velocity dispersion relation. The proportionality between the supermassive black hole's mass and the host galaxy's stellar velocity dispersion is an observed fact, but the exact physical mechanism that enforces it is still unclear. The mystery lies in how the black hole, whose sphere of influence is tiny compared to the galaxy, can communicate its size and regulate the star formation of the entire galactic bulge. This question of active galactic nuclei feedback is a central mystery in galaxy formation and evolution. The maximum spin rate that a black hole can achieve is determined by the balance between accretion and gravitational wave emission, but the actual distribution of spins in the universe is still a mystery. Black holes can spin up through continuous accretion or spin down through asymmetric gravitational wave emission. The observed distribution of high-spin and low-spin black holes will provide crucial information on their growth history, whether they grew through many small accretion events or a few large mergers. The precise endpoint of the final black hole evaporation remains a mystery. While theory suggests a final explosion, the fate of the last few fundamental particles and the final structure of space-time after the event are questions that push the limits of particle physics and quantum gravity. The final moment of the black hole is paradoxically the moment that contains the greatest information about the deepest physical laws. The theoretical possibility of super-Eddington accretion, where a black hole consumes mass faster than the radiation pressure should allow, is still a mystery. This rapid feeding is necessary to explain the massive quasars in the early universe. Scientists hypothesize that mechanisms such as thick, optically opaque accretion disks or powerful outflows could shield the inner disk, allowing for hyper-efficient consumption. But the exact physics are still being modeled. The question of whether black holes are truly the most efficient energy source in the universe, converting 42% of mass into energy, is a philosophical as well as physical mystery. The immense efficiency highlights the power of the gravity well surpassing fusion. But the possibility of even more efficient theoretical processes or undiscovered physical laws that could surpass this limit remains an open-ended question. The ultimate mystery of black holes is their role as a cosmic laboratory for general relativity. Every property and behavior we have observed has confirmed Einstein's theory. The remaining mysteries, the singularity, the information paradox, are the quiet, powerful signs that general relativity is incomplete and must eventually be superseded by a deeper, more profound theory of existence. We let the quiet, persistent questions of the final black hole mysteries settle gently in our minds. The unseen, the infinite, the unproven. These are the quiet edges of our knowledge, the beautiful boundaries that invite deeper contemplation. As we drift toward the final moments of our cosmic journey, we prepare for rest, contemplating our own small place in this vast, mysterious cosmos. We have completed our long, quiet journey through the deepest structures and most profound mysteries of the cosmos. We have drifted from the event horizon to the singularity, from stellar nurseries to the unimaginable future, exploring the bending of space, the slowing of time, and the gravitational language of black hole mergers. Let your mind feel full of this quiet knowledge, and let your body relax completely, releasing all effort. Think now of what we have explored tonight: the event horizon, the absolute boundary where time is stretched and information is sealed, the singularity, the point of infinite density, where the laws of physics collapse, the accretion disks shining with the brilliance of matter, meeting its inevitable end. We have seen the supermassive black holes, anchoring galaxies, and the subtle quantum dance of quantum decay, promising their slow, distant fade into nothingness. You are a part of this quiet, immense story. The atoms that make up your body, the carbon, the iron, the oxygen were forged in the hearts of stars and scattered across space in cataclysmic explosions, the very process that gives birth to black holes. Your existence is deeply intertwined with the cosmic cycle of creation and collapse, matter and gravity. The same physics that dictates the fate of a galaxy is at work in the quiet rotation of your small, blue planet. The final truth of the black hole is that it is not merely a destroyer of matter, but an essential regulator of the cosmos. It prevents runaway star formation, anchors the galaxy, and drives the most powerful gravitational events in the universe. It is the necessary contrast to light, the ultimate container of mass, the quiet proof that the universe requires both extreme presence and profound absence to achieve its stability and complexity. As you prepare for rest, let the immense scale of the cosmos bring a sense of perspective and calm. Your worries, your efforts, your daily thoughts are small things against the backdrop of billions of light years and trillions of years. Feel the gravitational time dilation working on your perception, allowing time to slow down, letting the past day fade into the background. There is no need now to hold on to every fact or every mystery. The information paradox can remain unsolved. The singularity can remain a secret. The deepest parts of the universe, the vastness, the darkness, the silence are the most peaceful. Allow your consciousness to soften, moving from the active thinking of the waking world to the passive, restorative state of sleep. Imagine yourself floating gently in the darkest, quietest corner of space, far from any star. You are weightless, suspended in the gentle flow of space-time, enveloped by the faint, cool whisper of the cosmic microwave background. You are safe, you are still, and you are part of an immense, beautiful, and eternal pattern. Let your breathing become deep, slow, and rhythmic. Let your thoughts dissolve like the last traces of a fading star. Let your body relax completely, surrendering to the pull of gravity and the peaceful depths of the night. The universe is vast, and you are resting. Thank you for journeying through the cosmos tonight. Good night, and may your dreams be filled with quiet wonder.